At 2,200 meters above sea level in the Himalayas, you are surrounded by sheer drops, volatile winds, and a staggering lack of oxygen. This is a landscape completely hostile to human infrastructure. Commercial aviation relies on three non-negotiable foundations: massive expanses of perfectly flat land, thick, dense air to generate lift under the wings, and ground that will never shift under the weight of a 70-ton aircraft. A Himalayan summit offers absolutely none of those things. There are no vast plains, the atmosphere is dangerously thin, and the geology is a chaotic mix of fractured rock and loose soil. In this environment, the margin for error is zero. A single miscalculation in soil density or a slight misalignment of a runway guarantees catastrophic rockfalls, massive structural collapse, or an aircraft overrunning the edge of a cliff. So how do engineers actually conquer the rigid laws of geology and physics to safely land commercial jets on a jagged, isolated peak? The first obstacle they face is the rock itself. To create a level canvas where nature never intended one, construction crews have to violently reshape the mountain's geometry. This diagram illustrates a brutal but effective mathematical technique called cut and fill. Excavators and blasting teams break off the highest sections of the summit. That fractured stone is then repurposed to fill the deep, empty valleys surrounding the peak, eventually forming a single continuous flat line. But loose rock cannot support a runway. The filled areas must be carefully compressed by heavy rollers, layer by layer. The material is crushed into a solid, dense block, because any uneven distribution will cause the future asphalt above it to sink and crack under the crushing weight of a landing jet. Before a single explosive is set, engineers conduct exhaustive geological surveys. They map hidden fault lines and measure slope angles to dictate exactly which sections of rock are safe to blast and which must be left intact to maintain the mountain's structural integrity. Engineers aggressively disassemble the mountain's geological anatomy and rebuild it into a mathematically calculated platform. Once the flat plateau is established, an entirely new physical enemy emerges: gravity. Millions of tons of newly compacted soil and pavement are now perched on a precipice, naturally inclined to slide straight down the slope. To hold the earth in place, engineers construct massive reinforced concrete retaining walls around the entire perimeter of the artificial airfield. Looking at this cross-section of the plateau edge, you can see how these massive walls stay upright. Crews drive giant steel rock anchors horizontally through the retaining wall, pushing them deep past the loose soil and locking them directly into the ancient, stable bedrock holding the mountain together. Down below the walls, any exposed, jagged rock faces are highly vulnerable to micro-collapses. To prevent this, workers wrap the jagged edges in heavy-duty steel mesh, which is then sprayed with a thick layer of concrete known as shotcrete, effectively sealing the cliffside. This giant anchored exoskeleton actively grips the summit, using structural tension to defeat the constant downward pull of gravity. With the ground secured, engineers have to account for their third enemy, the thin air and brutal elements of the high-altitude sky. High altitude drastically changes the physics of flight. At 2,200 meters, the atmosphere is sparse. This causes aircraft engines to produce significantly less power, and the wings to generate much less aerodynamic lift. This split-screen diagram highlights a punishing paradox for the engineers. Because planes struggle to generate lift in sparse mountain air, a mountaintop airport actually requires nearly twice the runway distance to achieve takeoff compared to an airport at sea level, a massive demand in a place where space is the most limited resource. That extended runway must also survive extreme weather. Crews install advanced water management systems with deep drainage channels designed to rapidly divert flash-melting snow and heavy rain before the water can seep in and undermine the pavement. Every structure visible up here, from the elongated tarmac to the heavily reinforced terminal building, is designed specifically as a fortified survival structure to withstand the punishing elemental forces of the Himalayas. To make this sky fortress functional, a new macro-infrastructure ecosystem must be carved out of the slopes. Trucks, fuel, and passengers rely on an intricate network of viaducts, tunnels, and sprawling access roads navigating steep switchbacks to reach the summit. After years of blasting and heavy paving, the ultimate test arrives as the very first commercial jet slowly descends. The complex network of retaining walls and compacted fill holds firm, allowing modern 70-ton aircraft to safely operate against the traditional Himalayan backdrop. By reducing travel time from days to hours, this single runway links these valleys to outside hospitals and markets, allowing emergency rescue teams to reach the most remote peaks in minutes. This impossible airport proves that humans can adapt to Earth's most extreme environments. They succeed not by ignoring or bulldozing over nature, but by intimately understanding and out-engineering the mountain's most powerful forces.